Okay, so what am I going to do to solve this problem?
AROs.
Okay, I don't have a matrix yet, so what?
I can't remember.
Pardon?
We can make.
We make a matrix out of this, right? And how do we build a matrix?
One.
Each vector goes into the columns. Now let's be careful here. So what's the first column going to be? 1, -2, 0, thank you. And then 3. Notice there's no x squared there, right? What about the second polynomial? What the second column? What's that going to be? Okay, good. And what about the third one? Okay, and the fourth one? You're doing a good job, so.
Okay.
Anybody else want to give Megan a break?
5.
-8.
Okay,
1 and 2.
got it, perfect. And we augment with all zeros, beautiful. Okay, so we do put all zeros there. Wow, that is the matrix. Okay, so here's what we're going to do because we're all not wanting to get too bored out of our minds. I'm going to help you, if I can find it, I hope I have this, tell you what this comes down to. Yeah, so I'm going to do EROs. I'm just going to tell you what the row reduced form is. Can I do that? Let me just tell you what the row reduced form is. The first row doesn't change. The second row is going to be 0, 1, -1, -3, -2, and 0. And the third row is going to be 0, 0, 0, 1, 1, 0. And the last row is going to turn out to be all zeros. Remember, all zeros is not really the key. But that is what it comes down to. Okay, so let me just see here. Sorry, I need to send somebody a little message. Okay, so you guys can think about what the conclusion is going to be from that. Okay, so what do I want to do next?
Throw out other ones.
Maybe always circle your pivots. I mean, that's such an easy thing to do, and I see a lot of people not doing it. You should always circle your pivots. And then the unpivoted columns are the ones that are creating the linear dependencies. So that would be columns 3 and 5. So if I throw out, if I go back, if I throw out the third and fifth polynomial, I will get my answer, right? These 3 polynomials are a basis for V. Don't be fooled into thinking that since this is 4-dimensional, that you're going to get 4 vectors at the end of this, right? Because these vectors don't necessarily span all of P3 of R, even though seems like there's a lot of vectors and they're all in P3 of R. Turns out they only span a 3-dimensional subspace of P3 of R. Yeah. So that's how you do it. You're basically taking a spanning set and throwing away dependent vectors so that you're left with a basis. Okay, so hopefully that didn't seem too bad, right? That's kind of something that you've seen some good examples of. Okay. What do I want to do here? I don't need to do number 8. You guys can totally do that one on your own. Do you know how to find a basis for the row space and column space of a matrix? I haven't talked about that. That's not a hard thing, but so this is number 4 on the sheet. We didn't do this one yet either. Number 4, I just have this matrix A equals -1, 0, 1, 3, 0, -3, and 1, 0, -1. So I have that. You know how to find a basis for the row space and the column space? Remember what you do?
Row reduce.
row reduce it. By the way, you probably noticed that all three rows are multiples of each other. So I can just put the basic first, I can take the third row, put it first, and then zero out everything else, right? So that's my row reduced form. So what's my basis for my row space?